Now we're going to begin our discussion on abstract data types or abstract data structures. And we'll start off with collections and more specifically a stack. Those of you that are taking CSC240 Computer Org at the same time as this class, you obviously have me because I'm the only professor teaching that course. We're going to spend a lot of time implementing a stack at the assembly and machine language level. So this is the abstract data structure that I'm most familiar with and have worked most extensively with. This chapter will discuss terminology regarding collections. We'll also get into the Java Collections API and the abstract nature of collections. And I'll add in a review of abstraction, which was covered fairly extensively in the prerequisite courses for this. And then we're going to drill down on a stack, which is an abstract data structure that follows a set of rules. We'll talk about it conceptually, how it's used to solve problems, many different problems in computing, and we'll look at an implementation of a stack using arrays. A collection is an object that holds, organizes, and manages the access of other objects. It has to provide operations for accessing and managing its elements, and that's a key term. We're going to talk about the elements in a collection, and more specifically, very quickly, we'll discuss the elements within a stack. There's many standard collections already defined. Some are linear. You'll see the stack is linear with a LIFO protocol, and we'll get to that in a few minutes. And others are nonlinear. Here we have a graphic depiction of two hypothetical collections. The one on the left is obviously linear, and the one on the right is nonlinear. Linear meaning you have to access, well, let's look at the stack. You have to start at the top and access the element on the top to get to the element right below the top, and then that becomes the element on the top once you've popped off the previous top, and et cetera, et cetera, et cetera. So it requires linear access. And the analogy I always use for a linear access collection when I'm covering the stack in CSC240 computer organization is the plate dispenser at a buffet. You have linear, one at a time, one after the other access to the plates in that dispenser. That dispenser also uses the same management protocol as a stack, which is LIFO, last in, first out. The last plate in to the stack or the dispenser is the first plate out. An abstraction hides the details of implementation to make a concept easier to manage. And we've talked about a stack briefly, last in, first out. There are many ways to implement a stack so that it follows LIFO, last in, first out protocol. All objects are abstractions in that they provide well-defined operations through the interface, access to the methods. They hide or encapsulate the object's data and also the implementation of the operations, i.e. the methods. So over time, it's become pretty obvious that an object is an excellent way to implement a collection, an abstract collection, obviously. So here we have some key terms. A data type is a group of values and the operations defined on those values. An abstract data type is one that isn't predefined in the programming language. A data structure is a set of programming constructs and techniques used to implement a collection. However, the distinction between abstract data type, data structure, and collection is often blurred in casual use. The difference between the three is minimal. Here we have a graphic depiction that helps us to differentiate between a class that uses a collection, the class that implements the collection, and the interface used by the class that's accessing or using the collection. And typically, the interface is the set of methods that the class provides external access to. We've already discussed that the classes provided with Java are in the Java API, the Application Program Interface. However, there's a subset of those classes that supports collections, and that's called the Java Collections API. And as we start to implement, or I should say, analyze and implement a particular collection, we'll also review all the support provided in the Collections API for that particular collection, such as the stack, which will be the first collection we're going to work with. A stack is a collection. It's a collection that is included in the Collections API, and it's used to solve many types of problems in computing. I think I've already mentioned that a stack is a linear collection, and we add and access those the elements of the stack, the elements in that collection, using a LIFO protocol. LIFO stands for last in, first out. So the last element to be put on a stack or added as an element to the stack, and when that happens, it becomes at the top of the stack. It is the first one to be removed. In fact, it is the only element when it's on the top and it was the last in. It's the only element we have access to via the stack protocol. Here the author says, think of a stack of books where you add and remove from the top but can't reach into the middle, or the coin dispenser that you have sometimes in your automobile where it has a stack, spring-loaded stack for nickels, dimes, quarters. I don't think they have pennies, but you know what I'm saying. So the last quarter pushed onto the stack, and if there's 5 on that stack, the last one pushed on is the first one that's retrieved. And when we get to 240, CSC240, I actually have an exercise where we show a series of 5 or 6 coins. Let's say they're nickels, and the coins are differentiated by the date on the coin, 1957, 1973, and we actually demonstrate pushing them on the stack and then popping them off the stack. And as I mentioned, 3 key terms. Push is used to push an element onto the second key term, top of the stack. And then when we remove an element, we refer to that as popping the top element off the stack. Here we have the classic stack operations, and these will be implemented as methods used by the interface. Push adds an element to the top of the stack. Pop removes the element from the top of the stack. Peek examines the element at the top of the stack but does not pop it, which means it's still accessible. It's still an element within the stack. Is empty determines if the stack is empty, and size determines the number of elements on the stack. Here we have a short program that I wrote to demonstrate the stack protocol. And we're using the stack class that's built into Java. This is really straightforward. I'm going to use a stack to push two elements onto it. I'm going to pop them off, add them together, push the result onto the stack, just so that you can see the stack. Here I'm creating a new stack named nStack. It's an integer stack. I'm declaring a few integers, op1, op2, and result, and a new scanner object. And then within a try-catch block, I'm going to prompt the user to enter two integers. I'll solicit them through the scanner object and assign them to op1 and op2. I've got some breakpoints in here, you'll see in a second. And then we're going to call the push method, and we're going to pass a parameter of op2, push method, which will push the value in op2 onto the stack, and we'll do the same with op1. And then result will equal nStack.pop. Pop returns an object, in this case it's an integer, plus nStack pop. So we're going to pop the two elements off the top of the stack, and you'll see this happen. And then we are going to push the result back on the stack. So I'm looking at this now. I could even put a breakpoint here so you could see the stack at various states. And this is all in a try-catch block. And at the end, I'm going to pop the result off, and I'm going to try to pop again, which will throw an exception that will catch and then report back. So let me run this, step into mode. It's going to ask me to enter two integers. I don't know, we'll say 45 and negative 50. Okay. So here we are at our first breakpoint. We've pushed the second, or op2, onto the stack. So let's come down here and look at our variables. And I'm going to have to expand this a little bit. Okay, so here's our stack. At element 0, I've got negative 50, which is the second operand, because we're pushing op2 first and then op1. If I proceed, step over the second pop, there we have negative 50 and 45. 45 is now on the top of the stack. Result, and I'm going to actually use the pop in the expression. So nStack pop will pop the 45 off, and then the negative 50. So we'll add 45 and negative 50 together. We'll assign that result to result, no pun intended. And then we're going to push result onto the stack. So there's a lot of moving parts all at once. So here we are. The stack is now empty. I've popped twice. Result now holds -5. Op1 and Op2 still hold -50 and 45, but they are no longer accessible via this stack. No matter what we try, we cannot get to them. They are no longer accessible as an element of this stack. Now, for those of you that are going to go on and take CSC240, or the few of you that might have taken it out of sequence, those elements or those values are still there in memory, but given the protocol of the stack, they are inaccessible. You cannot get to them. And the next time we push an element onto the stack, it will overwrite the 45, and that will be gone from memory. It will be, even with CSI techniques, it's gone. And then we push another element on the 50. So let's proceed. We're going to now push the result onto the stack, and there's our -5 on the stack. Then we're going to system.out.println line result equals, and then we're going to execute peek. Peek is a method that returns the value on the top of the stack but does not pop. That's why it's called peek. We're just taking a peek. If I go to output, there it is, result equals -5. Here we go. One pop. Now notice the stack is empty. I'm going to now try to execute pop again. And because the stack is empty, it's going to throw an exception, and it'll be caught by the try catch block, and we'll get this message printed to the console. And if I go back to the console, whoops, sorry, there's my illegal pop. Hope this was useful. If you have any questions, of course, you know what to do. As we further explore collections, we will be using many object-oriented concepts, many that we've already covered, and some new ones. We're going to rely on type compatibility rules, interfaces, inheritance, and polymorphism, all of which were covered extensively in the prerequisite course for this course. So you may want to review these concepts. And we'll also rely on a programming mechanism introduced in Java 5 called generics, which are particularly necessary and appropriate for implementing collections. So think about a scenario where we define a stack that holds object references. And by doing so, we can add any object to the stack as an element. However, what if we lose control over which types of elements are added to the stack, and then we'd have to cast elements to their proper type when removed? A more efficient solution is to have a class that is based on and this is a key term, a generic type. The type is referred to generically in the class, and the specific type is specified only when an object of that class is created. So to create a generic type placeholder, we specify in brackets in the class header. So in this example, we're using T for type, or we could use E for element. And these are standard but not hardwired requirements. Standards are strong recommendations, and we're going to use T and E extensively in these examples in this lecture. Then, when we need a box, an object of the box class, it's instantiated with a specific class, in this case box, instead of the T. So box, widget, box equals new box, widget. I'm sorry, box 1 is the object reference variable. Now box 1 can only hold widget objects. If we try to add anything to the box that is a non-widget, the compiler will give us an error. Furthermore, whenever an object is removed from the box, it can be assumed, safely assumed, to be a widget. Then, using the same class, another object can be instantiated. Here, box 2, the box 2 object can only hold gadget objects. So therefore, generics provide better type management control at compile time, and they also simplify the use of collection classes. Now we're going to take a look at a situation where a stack can be used to help solve the problem of evaluating postfix expressions. A postfix expression is written with the operator following the two operands instead of between them. So 15, 8 minus is the equivalent of the traditional, and I just learned this, infix expression 15 minus 8. I had never heard that term before, infix. Obviously postfix I was aware of, but infix is the default algebraic protocol we use. I remember when I was an undergraduate many years ago, some of my friends, we were all studying engineering, computer science, architecture, etc. And where I did my undergraduate work, I actually went to the College of Engineering, Computer Science, and Architecture. So everybody was grouped together. And many of my co-students, classmates, purchased a Hewlett-Packard calculator with what was then called reverse Polish notation. And you can Google that. It's not slang. It really isn't. And I did very well in math and aced all the calculus and differential equations and linear and discrete, all that stuff. But I always avoided buying a reverse Polish notation calculator, which is now called postfix. So I guess it was always called postfix. But the calculators that implemented postfix used what was called reverse Polish notation. I know I'm getting off on a tangent here, but postfix expressions eliminate the need for parentheses to specify the order of operations. And this is where I wish I had more experience in the reverse Polish notation calculators, because this would be a little bit less or a little bit more intuitive for me. So the infix expression, 3 times 4 minus 2 plus 5 times 4 divided by 2, is the equivalent of this postfix expression, 3 space 4 asterisk multiplication, 2 5 plus minus 4 asterisk 2 slash. It is exactly the same, and using postfix notation eliminates the need for parentheses. So we're going to use a stack to evaluate postfix expressions. We're going to use a scanner object, and we will solicit the entire postfix equation into a single string. And then we're going to scan the string from left to right. And when an operand is encountered, we'll push it on the stack. When an operator is encountered, we'll pop the top 2 elements on the stack, perform the operation, then push the result onto the top of the stack. When the expression is finished, the value on the top of the stack will be the final results. So let's take a closer look. So hang on, there's a lot of moving parts to this slide in which we evaluate this postfix expression. And what you have is the postfix expression 7,4 minus 3 asterisk 1,5 plus slash asterisk. And then we're going to move from state to state to view the stack. So we don't get to an operation until after we've pushed a 7, pushed a 4, and pushed a -3 onto the stack. So the first state change would be an empty stack, then we push a 7, then we push a 4, and then we push a -3. And then we encounter an operation. Well, with each operation, we pop the 2 elements off the stack, perform that operation, and push the resultant back on the top of the stack. So moving from the first depiction of the stack where we have 3 elements and -3 is the top to the second, let's see what happens. So we hit the asterisk, we pop -3 and -3 and 4 off, and we multiply them. -3 times 4 is -12, and we push the 12 back on to the top of the stack. And there we are at the second state, if you will, with a -12 at the top and a 7 beneath it. Then we come to a 1, we push that onto the stack, and we come to a 5, and we push that onto the stack. And then a plus sign, which is addition. We will pop the 5 off, the 1 off, add them together. The resultant will be 6, and we will push the 6 back onto the stack. Then we have another operation, slash. So we're going to pop a 6 and a -12 off. We will divide the -12 by 6, and we will get 2. I'm sorry, -2. -2 gets pushed back on to the stack. Then we will hit a multiplication, -2 and 7, and that will yield, should have a last example of that, that will yield -14, which should be the result left on the stack. I'm going to run a program that implements a stack and the postfix evaluator program next, and we'll actually see how this works. Okay, students, hang on. There are a lot of moving parts on this one, and I'm going to be jumping back and forth between a few screens. So here we have the application which uses the collection through an interface, and the collection in this example is going to be a stack, and that stack is well managed in another class called the postfix evaluator. And so here we declare some variables in main, expression again, and an int result. We declare a new scanner and we initialize it, or connect it to the keyboard. And then we've got this do while loop, and we're just going to do it until the user opts out. So new postfix evaluator called evaluator, call the constructor. We prompt the user to enter a valid postfix expression, 1 token at a time, space between each token. Each token must be an integer or an operator. Okay, and then we use next line, and we move the entire postfix expression no pun intended, into this string expression. And then we call the evaluator object, calls the evaluate method, and we pass expression to it. And the result is returned to result. So that's really all the postfix tester program does. Now let's get into the postfix evaluator. We've got a new stack of integers. Okay, notice we are importing java.util.stack. That enables us to use the constructor for stacks. So then we've got the evaluate method, which takes a string, and in this case we pass the entire string, the entire postfix expression to this evaluate. A couple local variables, op1, op2 are integers, the result equals 0. We got a string named token, and we've got a new scanner named parser, and we're using that string as the source for that scanner. So while has next, while it can get the next token, okay, while there's still something left in the string, token equals parser.next. So if it's an operand, it will get the operand. If it's a operator, it will get the operator, and we simply evaluate if it is an operator. Is operator is a method that determines whether it's a plus, minus, asterisk, or a slash for addition, subtraction, multiplication, division. Those are all the operations that this postfix evaluator does. So if it's an operator, if is operator, okay, then we will go to the stack, we will pop an integer value off, and we'll use it, assign it to op2. We'll pop a second one and assign it to op1. Okay? And then result is evaluate single operator token char at sub0 op1 op2. Okay? Evaluate single operator simply has a switch statement. If the operator is add, we add the two stored in result, subtract, multiplication, etc. That's all it does. And then we're going to push the result onto the stack as a new integer object. So else, if it's not an operator, we're just going to simply push the integer onto the stack. So I've got quite a few breakpoints in this, so I'll be able to show you the stack in progress. And I'm also going to use this postfix equation, 7, 4 minus 3, asterisk 1, 5 plus. I might have to jump back and forth because I'm not good at remembering that many things at once, but we'll use that just like it was in the slide. So let's, no further ado, let's debug the file. First thing it asks us for is that postfix expression 7 space 4 space minus 3 asterisk 1 space 5 space plus. Okay, so I've correctly typed in the postfix expression, I think. 7, 4 minus 3, 1, 5. Yes. Now let's get started. Okay, so we're in that do while loop. We're going to step into the evaluator. If we look at the variables, okay, we can see the expression the string, there it is. The entire thing is captured. Now we're going to parse this and determine if we have an operand or an operation. And remember what it does. If you have an operand, it pushes onto the top of the stack, pushes on the top of the stack. If you have an operation, it pops the last two elements off the stack, performs the operation, and pushes the result on. So let's we will step into this. So here we are. Okay, we have expression was passed the entire string. Okay. Oops. Okay. Step into this while loop. So what we have token equals parser dot next. Step in, step out. So here's our stack. At this point in time, it's 0. Let's step in. Okay. Whoops. Here's our stack. It's size 0. We're going to push a new integer because that was not an operand. We're going to push new integer onto the stack. And there it is. There's our 7 pushed onto the stack. Okay. There's our 4 pushed onto the stack. There's our -3. So let's go back. Here we are. 7, 4, -3. Okay? There they are. Element 0, 1, and 2. The stack size is 3 right now. The top of the stack has a -3. We're going to hit an operation, asterisk. It will pop the -3 and the 4 off, multiply them, then push back on. Here we are. Okay, right now, we pop the -3 off. Okay, -3 is an op2. We're about to pop the 4 off. There we are, the 4 is off. And if we look at our stack, the only element on the stack is the 7. Now we're going to execute the multiplication and push the -12 onto the stack. And if you continue to do this, you'll see there's the 1, there's the 5 on the stack. Then we're going to come to an operation, and we're going to pop the 1 and the 5 off, add them to 6, push the result on the stack. Okay, the stack has the 7, -12, and 6. 7, -12, oh, here it is, 7, -12, and 6. I will continue an operation. There's our 7 and our -2, and I will continue. If you recall, that slide didn't really do it. There's our negative 14, and our negative 14 is on the top of the stack. Return the result. So now we're back in postfix tester, and result holds the negative 14, and the rest is just simply the expression equals negative 14. I know that's a lot of moving parts. There's no way you're going to understand this by just watching this lecture. And as you know, as you probably have guessed, well, maybe some of you didn't have me for 122. The files, the Java files for this project will be in the Canvas timeline. Here's what I suggest. Right this second, stop, download them, put them into a package, run them, put the breakpoints in, and see what happens as you enter various postfix equations. The postfix example uses the java.util.stack class. That class has been part of the Java Collections API for many years. Well, since the beginning of Java 1.0. And it implements most of the classic operations without a separate interface defined. You may notice there's not a lot of consistency regarding how collections are implemented in the Java API. So we're going to have to explore the relative benefits as appropriate. In some cases, we're going to implement our own. Here we see the relationship between java.util.stack class, the actual implementation of the stack holding integers, and then the postfix evaluation, which has a stack and methods necessary to perform the arithmetic operations in postfix format, and obviously the postfix tester, which is the driver program. The documentation style that we used in the postfix example is called JavaDoc. And JavaDoc comments are written in a format that allows the JavaDoc tool to parse the comments and extract key information, which is used to create online documentation in HTML about a set of classes. All the documentation in the Java API is generated this way. Next, we're going to go over the differences between a regular comment in a Java program and a JavaDoc comment. JavaDoc comment begins with slash, followed by 2 asterisks, and ends with asterisk slash. And within the JavaDoc comment, we use tags, which begin with the @ symbol. And these tags are used to identify particular information. So here we have an example of some of the JavaDoc tags: @author, @version, @param, @return. So we're going to start using JavaDoc comments within our class definitions. Here is a simple example of a JavaDoc for a method that we'll just say we wrote. There you can see the beginning, JavaDoc comment slash asterisk asterisk, immediately followed by the method description. On a new line, we use the @param to define or to describe the parameter or parameters. And we also use the @return to describe the return for this particular method. When should an exception be thrown from a collection class? This is a great question. Well, you only throw an exception when there's a problem specific to the concept of the collection, not its implementation or its use. So, for example, we don't want the user of a collection to worry about it getting full. So we must take care of that limitation internally during the implementation. However, if the user attempts to pop an element off of an empty stack, well, there's no way we can safeguard against that, because we want the user to be able to pop an element off the stack, and obviously we can't control it going to 0. If there's 10 elements on the stack and I try 11 pops, well, obviously when the stack is empty after the 10th pop, we have to throw an exception. There's no element on the stack, yet pop is clearly available to the user. As we discussed earlier, the API version of a stack doesn't have, nor does it rely on, a formal interface. But we will define one for our own use. So to distinguish an interface for a collection, we're going to use names that have ADT attached, ADT, abstract data type. And all of our collection classes and interfaces will define them as part of a package called JSJF. Let's take a closer look. Here we have a stack interface. Notice its declaration, public interface stack ADT. Interface is a reserved word. Stack ADT is the interface name. And we're using the generic type parameter, which means we're going to be able to instantiate stacks of whatever type we choose. And all we're doing is we're identifying the interface for the methods that will be fully implemented in another class. We got push, we got pop, peek, boolean is empty, that just returns a boolean, size, and the toString method. We're going to look at this in much closer detail, so just stay tuned. Now, I just want to remind you, a stack is an abstract data type. There is a stack class built into Java. It's been there since Java 1. But how that's implemented is abstract. We don't really need to know, right? So we're going to, in the next few minutes, or depending upon your time frame for viewing this, we're going to implement a stack using an array. And it's just one way of implementing a stack as an abstract data type. And here's the interface for that potential implementation of a stack. And you'd have push, pop, peek, is empty, size, toString, which is what we just looked at using the generic data type. So abstraction, inheritance is all at play here. So as I mentioned, we're going to explore implementing a stack using an array. So if we use an array as the underlying structure to store the elements in the stack, remember an array is statically allocated, its size. So we'll have to take into account the possibility that the array might become full. And also remember that an array of objects really stores references to those objects. So if we implement an array using, if we implement a stack using an array, it really becomes an array of object references. So you're probably thinking, if we use an array as the underlying structure for a stack, and we can't change the capacity of an array in Java once it's created, how are we going to make this stack dynamic? Well, the number of cells in an array is called its capacity. And if we want to expand the capacity of a stack, here's how we're going to do this. We're going to create a new larger array and copy the elements of the array that is at capacity into the new array. And if I remember correctly, the implementation that we're about to explore doubles the size of the initial array when creating the new array, and then stores the elements of the full array into the first 50% of the new doubled capacity array. So this is going to happen infrequently, and the user of the stack doesn't even need to worry about it happening. It will be abstract. You won't even know, and you won't see this. So let's further discuss the implementation of a stack using an array as the underlying structure. We're going to call our ADT implementation array stack. And our implementation will keep the bottom of the stack fixed at index 0 of the array. Remember, this is one of who knows how many potential implementations. And the implementation is going to be abstract to the user. As long as the stack follows the protocol, LIFO protocol for a stack, it really doesn't matter how it's implemented. And of course, there's some efficiency considerations. Okay. We're also going to use a separate integer called top to indicate where the top of the stack is, as well as how many elements are on the stack. In this implementation of this stack, we have elements. This is a state snapshot of the stack where elements A, B, C, and D have been pushed on in that order, which means at this state, the only element that is immediately accessible is D, because it's on the top of the stack. And in this particular implementation, we happen to be using top to point to or indicate the first open slot on the stack. Top could easily be 3. Top could hold 3, and then when we want to push, we would move the pointer and then store the element at the next index in the array. I'm stressing that these are implementation details that are really irrelevant to anyone who uses this stack because it's an abstract data type. Here are some early implementation details. This is an array implementation of a stack in which the bottom of the stack is fixed at index 0. You're going to have access to this fully implemented solution. Actually, not fully implemented, so I'm going to have you implement 2 methods as an exercise. But we've got public class array stack with the generic data type implementing the interface stack ADT. There's our default capacity set as a final or a constant at 100, an integer for top, and there is our generic stack. Next, we have 2 methods that create an empty stack. The first uses the default capacity, and the second has a parameter specifying, an integer parameter specifying the initial size of the array, which is the underlying structure of the stack. You might have noticed this on the previous slide. We're creating an array of a generic type. You cannot instantiate an array of generic type directly. Instead, you have to create an array of object references and then cast them to the generic type. So here's how we did that. We cast it as an array of generic type T, and we create an array of object. Excuse me. Here's how we take care of push, and we also have a method expand capacity, and you'll see how that works in just a second. So in the push method, we have a generic element as the parameter being passed to push, and if size, right, if the size of the underlying stack, which is the structure supporting, the underlying array is equal to stack dot length, then we call the method expand capacity. And what expand capacity does is just copies the stack to a new stack that's double the length. And this happens whenever we get the capacity, and it's the user of the stack doesn't even know this happens. So here's the actual push. The element passed as the parameter becomes the stack top. And remember, top in this implementation, remember, is the first unused space in the stack. And then we increment top. If the pointer for top in the implementation pointed to the top element stored in the stack, we would simply implement top first and then assign element to stack sub top. It's just a detail that is abstract to the user. Now, because the stack will expand its capacity if we try to push an element on a stack that is full, we don't have to worry about exceptions because we can keep on pushing elements, and when we get the capacity, it'll double the capacity, etc., etc. But pop could easily throw an exception, okay? If the stack is empty, you can't pop an element off the top of the stack if it's empty. So we have a method is empty, and if it's empty, we throw new exception, and that's taken care of. If not, top gets decremented, right? And then the return T result gets assign the element that's on the top of the stack. And remember, the top of the stack is pointing to the first empty, or I should say the first space above the top of the stack. Now in this case, the value is still there, but for a short instant or moment in time, it's not part of the stack. The top has been redefined, and we're now assigning that value that was the previous value at the top of the stack to result. Okay, and then we're assigning null to that top. So in this implementation, I think I actually might have said something that could be misleading earlier. In this implementation, we clean up the value, so it's not even there with some CSI techniques. It's assigned null. Thus, again, that's an implementation detail. And even if you didn't do this, there'd be no way via the stack to get to that element because of the LIFO protocol. Then we simply return result. Then we have the method peek. Peek can also throw an exception because if it's empty, you can't peek at the top element. If it's not empty, we return the stack top -1. So in this implementation, we have two state snapshots. After we push element E onto the top of the stack, the pointer top now points to index 5 in the array, and which is the underlying structure of this stack. And there's E at 4. And after we pop it, now remember the sequence of events that occurs when we call the pop method. Top moves from 5 to 4. Okay. And then 4 gets assigned to element. I'm sorry, result, I think, was the name of the variable. And then we assign null to top. So we actually do delete or eliminate the value in memory. That's not a requirement. And when we get to 240, you'll see that we can do that as part of an implementation, but we don't have to. And I'm 100% positive the first, second, and third implementations of stack that we use in machine language in 240, we don't do that, because remember, there's no way to get to that value given the stack protocol. When a pop or peek is attempted and the stack is empty, the method throws an empty collection exception. Empty collection exception is defined to extend runtime exception from the exception class. So by passing a string to its constructor, this exception can be used for other collections as well. Here we have the public class empty collection exception, which is a child of runtime exception, extends runtime exception. And you could see when you pass a string to this, it will just simply add the collection is empty, the whatever that is, the stack, whatever, is empty to the exception that's thrown. So we're going to finish this lecture with a somewhat developed implementation of an abstract data type stack. This is also your assignment or one of your assignments for this week or this section of the class. I'm going to give you an overview of this application that I've written, but there are some pieces missing, and there's a rubric also for this assignment, this project. So here I have the front end of this. It's called array test, and that's what we're looking at right now. And it has the main function in it, and it creates a new array stack object that stores strings. But you're going to see later that we're using generics, the generic data type. So this could easily, my main function could easily, with the back end that we have here, the interface and the actual class implementation, we could easily have instantiated an array stack of integers, doubles, floats, whatever, chars, etc. So this simply uses a switch to present a menu system that you'll see in front of you that calls all these options. I'm still debating whether or not I'm actually going to give you this file or just let you see the beginning here in this demo. So, and then we have stack ADT, and I want you to take a look over here. So you're going to see the members of each of these. This is the interface. Okay, we have an interface, a stack abstract data type using the generic T, and it is an interface for the methods in the class, which is the array stack class that I've created. Is empty, peek, pop, push, size, toString. There is one missing, and I believe it's size, toString are not fully implemented. That I'm leaving to you. So, and then here's our full implementation of the array stack, all the members. You've got the stack, you've got a final or constant default capacity int, and we have an integer named top to keep track of the top of the stack. And in this implementation, well, actually, I'm not going to say that. In this implementation, I want you to pay close attention to what top or how top is implemented. And remember, top doesn't have to be implemented to point to an empty element, the next element to take a push. It could point to the top element or the last element that was pushed onto the stack. These are implementation details that are abstract to the user of the stack. So here I have the interface just simply in the documentation for each of the methods, and then here we have the full implementation of the class array stack, which implements stack ADT. You'll notice that we're using generics. So I'm going to run this just so you can see. Well, I actually have a run there, but I'll run it live here in this video. So there's our menu. So we can push. Remember, this is an implementation of a stack of strings. So I'm going to I'll push a few strings. Okay, I just pushed William onto the stack. I'll push another string name. Okay, I'll push another string name. Okay, so I believe peak is, so now if I were to, let's pop, let's type a 2 and we'll pop, okay? The element popped off of the stack is Justin. Okay, that was the last element pushed onto the stack. If I peek, I'll now see the top element is Stephanie. If I pop, Stephanie's popped off. If I peek now, it should be William. And if I pop now, let's not do that yet. Let's push another element. Push the name Harper. And if I peek now, Harper is at the top of the stack, and I can pop 2 elements off the stack. There's Harper. There's William. Now if I try to pop again, I'm going to get an exception. Okay? So I need you to fix that. I need you to make sure that that doesn't happen. You can't pop off an empty stack. And that can easily be taken care of. Here's some other, let me run this again. Okay. If I choose display, I believe I have that, okay, not yet defined. I need you to implement the method display in the interface and in the class so that it will display all elements on the stack in a single, on a single line. I think size is also part of this, and that is used, it's a method that's used. Yeah, size is not implemented. I don't believe isEmpty is not implemented yet, which is why we're getting these exception errors. These should be fully implemented so you don't get any exceptions thrown. I will give you an exceptions file. It's here. You're going to need that while you're running it before you have all of these issues resolved. Of course, if you have any question, don't hesitate to contact me. Thanks for watching.